Welcome, everyone. My name is Gabriel Fierro, and I'm a sixth-year PhD student in the Computer Science Department at UC Berkeley.
And I'm Keith Moffett. I'm a fifth-year PhD student in the Electrical Engineering Department at UC Berkeley. And this is joint work with Jasper Pakshong and Sasha von Meyer, and we'll be presenting an extensible software and communication platform for DER management. So over the past couple decades, we've seen a proliferation of distributed energy resources, or DER, which includes solar panels, electric vehicles, battery energy storage, and controllable loads. And up till this point, largely DER have been tolerated. But as we move to deeper penetrations of DER, we're going to have to start relying on the DER. And in order to rely on the DER, we'll have to move towards mechanisms of distributed grid control, which allow the DER to respond quickly to local measurements while still coordinating with other controllers and/or central optimization. So distributed grid control requires a software and communication platform, and that's essentially what we'll be presenting in this talk. We've created the Distributed Extensible Grid Control, or DEGC, software and communication platform, which provides a platform for general distributed grid control applications. So the most common example of distributed grid control is Volt-VAR, or volt-watt control. And Volt-VAR and volt-watt control is basically the modulation of local reactive and/or real power injections based off local voltage magnitude measurements. And while Volt-VAR control is presumably a benign form of supporting the voltage on a distribution grid, if many inverters are actuating similar Volt-VAR curves, and those curves are not tuned or taking into account the fact that there are other controllers on the network, it can actually lead to network instabilities. So even in the basic case of Volt-VAR control, it's important to coordinate among assets, and thus a communication framework is necessary. In addition to Volt-VAR control, we introduced Phasor-based control earlier this year. And Phasor-based control is a very aggressive form of distributed grid control in which there are distributed nodes throughout the grid which receive phasor targets from a central optimization. And each of those nodes enforces the phasor target by modulating the real and reactive power commands of the subordinate DER, such as battery energy storage or controllable inverters or controllable loads. And PBC is a particularly challenging distributed control application because it requires real-time communication of PMU measurements. So those PMU measurements are ingressing at a rate of 120 hertz and have to be communicated from the reference PMU to the local PM or to the feedback controllers because in order to define a phasor, you need both a local phasor measurement and then also the reference PMU measurement. So PBC is essentially a very challenging form of distributed grid control, which will eventually demonstrate that the DEGC platform can support.
All right, so now we're going to give you an overview of the kind of challenges that are going to arise in these distributed control settings. First up is just the heterogeneity and the impermanence of distributed energy resources. There's many different types of DER, PVs, EVs, battery energy storage that all have their own interface. They all have their own API. Oftentimes they talk over different kinds of networks, Wi-Fi, Zigbee, BACnet, LAN talk, Modbus. And so the platform is going to have to deal with that kind of heterogeneity. Further complicating this is the fact that DERs are constantly going to be added and removed from the network. And so in order for this platform to support the wide array of those resources, adding and removing those DERs needs to be somewhat lightweight and agile. Another complication, which I just alluded to, is just the communication network inconsistency. Even so, within a local site, you're probably going to have a whole myriad of different networks and protocols and APIs that you're going to have to deal with. But across the wide area, when you're starting to deal with trying to transfer measurements from one microsync phasor to another microsync phasor in order to make the right control decisions, you're going to have to deal with the fact that these wide area networks are usually not very reliable. And so making sure that the software you're developing can be implemented robustly in those settings is something that the platform is going to have to provide. And lastly, it goes without saying that the electric grid is critical infrastructure for modern society. And so anything that's going to be measuring or actuating that grid or the resources attached to that grid is a potential target for cyber attacks. And so the platform is going to have to make it um, possible to communicate and to configure and reconfigure these resources to such that they can communicate securely and that data is private in transit. And so this brings us to DEGC, the Distributed Extensible Grid Control Platform, which consists of a family of software, libraries, databases, and control communication platforms for implementing and deploying DER control. There's essentially two main components, which we'll dig into. The first component is the process, which is essentially where most of the real work gets done. And the process is any piece of software that's going to be interacting with the underlying DERs. It's going to be implementing control. It's going to be sending and receiving actuation commands. And the goal of the process is to try and abstract as much as possible the heterogeneity of all the different resources and controllers and just entities that are in this that are in the DER space. The process is going to be interacting with a message bus, which is going to perform the actual communication in both the local and the wide networks. And there's going to be four essential flavors of a process that we'll talk about: the controller, a remote actuator, a data source, so something like a microsynchrophaser, and a data sink, which would be something like a data historian. The other component is the message bus, which is going to implement secure and reliable transport between all of the distributed resources and distributed processes that are in the platform. So how does DEGC address the DER challenges? We'll provide you an overview here, and then we'll dig in the following slides. So in order to address DER and heterogeneity and impermanence, we're going to be using just the innate features of a pub-sub bus. And what a pub-sub message bus does is it decouples the data producers and consumers, which makes it possible for a very popular microsynchrophaser to be consumed by a large number of controllers without needing to go into a tremendous amount of configuration and setting up networks and firewalls and traversing local area networks. And so coupled with that, the fact that we're building on a layered software architecture means that it's very easy for us to construct and produce abstractions that make it easy to create the kinds of controllers and to interact with different kinds of devices and DERs as we need them. As I just said, the communication network is going to be providing us through the message bus a reliable transport over the wide area network so that the code that we write needs to deal very little with those kinds of reliability issues. This is going to allow us to implement communication over a wide array of networks, interfacing with a wide array of different communications schemes. That's sort of the last mile where you're actually going and talking to a device, as well as a array of diverse network conditions such as traversing LANs and firewalls. Lastly, to handle security and privacy concerns, we're going to be leveraging a recently developed system for decentralized authentication and authorization that's actually integrated with the message bus that provides us some really nice primitives to be building on top of. And so a detailed discussion of that is far beyond the scope of a 20-minute talk, but we'll give you sort of a high-level overview of what that provides. Okay, so we'll start building up from the DEGC process. And what a DEGC process is it's essentially an extensible software library built using a layered architecture that right now is implemented in Python, though really there's nothing preventing us from taking these lessons and applying them to compatible frameworks implemented in other languages. And the key here is that the DEGC process is built up from a modular set of libraries which provide functionality that makes it easier to construct higher level processes and higher level pieces of functionality that can build on the layers below. So the lowest layer in this library is the communication layer. And what that does is it handles all of the communication to and from the pub sub bus. It handles the handshakes, it handles the validation of security, and it's going to provide the easy API calls for being able to subscribe to a stream of messages from everywhere, publishing messages to a topic, and to be able to invoke functions on some periodic basis. Built on top of that are the parallel controller and data layers. And these are essentially libraries that make it easy to construct controllers and other data-oriented processes, being able to broadcast targets, for example, being able to implement iterative control algorithms, being able to trigger callbacks when you receive an actuation command. These are all pieces of functionality that are implemented by the controller and data layers. And finally, there's the application layer, which is constructed on top of these other layers. And this is where the actual sort of domain-specific and application-specific and device-specific code goes. So this would actually interact with a smart inverter, interact with the load bank. It would implement your Volt-VAR or your PBC control. Basically, anything that you need to do becomes very simple. You just focus on the implementation that you need to do, and then the layers take care of abstracting away all the rest of the communication and infrastructure that underlies that. And so now digging into how the process interacts with message bus-based communication. So a message bus or publish subscribe based communication essentially provides the abstraction of asynchronous local communication. And what this means is we don't need to deal with exchanging IP addresses and ports. We don't need to deal with opening up your firewall to make sure that someone can get something through. Really just lets you deal with, instead of having to know where on the network a data source is or where on the network a controller is, you can instead just interact with that transparently through a topic, which is just a hierarchical name that refers to the stream of data that's going to be produced by a data producer or consumed by a data consumer. And so, for example, here, if I want to subscribe to the one of the Volt channels on a micro PMU that's at node 675 in my network, I might subscribe to a topic called /UPMU/UPNU 675/L1. Now, the actual data that's going to be carried on the message bus are going to be messages. So it's a discrete datagram with an extensible message format. This is built on the protobuf format, which was pioneered by Google. And so this has allowed us to capture IEEE C37 frames from the micro PMUs. We've delivered open ADR messages. We can deliver control targets for a variety of different control schemes, sensor readings, actuation messages, and so on. And so what does this message bus actually look like? How is that implemented? So while processes just see the abstraction of a single unified message bus, underneath the covers, there's actually a whole distributed network that the message bus is building on top of. And so we call this a tiered architecture because, in contrast to most traditional PubSub networks where you just have one big process that's sitting up in the cloud that everyone talks to, we actually have local little routers that take care of sending messages within a local site or within a local area network, which is typically more reliable. And then you've got a designated router or another process that's in the cloud, which handles routing messages between all of these different sites. And what this means is that it's pretty easy to stand up a new site, install a new machine, which can run on a Raspberry Pi, a small commodity server, or a laptop, and attach new resources with relatively little reconfiguration of existing networks, firewalls, and other processes. And so how do we implement reliable delivery on a message bus? So that, again, this is not typically a feature that you find in a lot of message buses, but essentially we're going to leverage the tiered architecture to make sure that we're providing secure and reliable communication within a site. So even if your node is disconnected from the internet, you're still able to exchange messages between all of those processes and resources at that local site, and use queues between each of these components that are distributed so that when communication is broken, delivered messages can be buffered and then redelivered when communication is reestablished. One of the complications here is that you need to be able to differentiate between messages that are delayed and messages that were delivered. And so what the platform does is it tags all of the messages with queue timestamps so that you're able to differentiate at the controller to make sure that you're doing proper filtering. And of course, we can tune the queue sizes and the eviction policies here to make sure that we're not buffering up too much data. For instance, it might make sense to, once you've got more than an hour of buffered data, to discard that to make sure that we're saving disk space for more recent and thus more relevant data. Lastly, I want to give you an overview of the message bus security. Again, this is a much deeper topic, so this is a fairly high level overview. But essentially, if I have some data producers, say a microsynchrophaser that's publishing some data, right, on some topic, and I've got some control process, might be implemented in Python, that's going to be consuming that data and producing some control decision. I want to make sure as a system administrator that the micro PMU is actually who it says it is, and it's not some false process that's sending in data that's trying to cause some issue. And that I also want to make sure that the control process is one that's actually allowed to receive the data that's being transmitted by a real microsynchrophaser. And so what's going on underneath the covers as all of these things are running is there's this whole essentially a permissions graph. And so the permissions graph is something that's been pioneered by the Wave authentication system, which was recently developed at UC Berkeley and published last year at Usenix. And essentially what it does is it forms a network of delegatable permissions that doesn't rely upon a central authority or a central database to store the entire list, authoritative list of who can do what. And so what this means is that this it's possible to delegate these permissions from a grid provider who maybe has visibility or permissions over everything, delegate it to a project manager who then delegates the ability to manage permissions to a microsynchrophaser, to a system administrator, and then to a lab manager, and thus to a grad student who actually goes and writes the control code. And if these people lose their keys or their passwords, or as people leave and enter the organization, this whole network of permissions can be fairly easily repaired. It also enables end-to-end encryption. It sort of defaults to private, and so it makes a lot of sense for being able to control and configure and manage DERs, which may indeed cross at different administrative boundaries. The last thing that's important to mention is that the message bus actually implements this security solution inside the routing infrastructure itself. So it's not just that processes have to double check these things. As those messages are getting forwarded throughout the network, the message bus is being sure to drop any unauthorized messages before they reach vital processes and vital DERs.
So we demonstrated the DEGC platform on real hardware at Lawrence Berkeley Labs Flex Lab test site. And the test site consists of an Opal RT grid simulator that's here in the box on the right, an Amitech power amplifier, 4 PMUs, and actuation hardware, including a solar edge inverter, solar panels, a battery, and a controllable load bank. Specifically, we chose PBC to demonstrate the control platform due to PBC's demanding PMU data communication requirements, as we mentioned earlier. Both the supervisory and feedback controllers were implemented as DEGC controllers, and the PMUs were implemented as DEGC data sources. The table at the bottom of this slide describes the details of the message bus from the demonstration. And it's important to note that each PMU message contains 120 measurements. So the 300 messages per minute on the right side for the PMU data source actually corresponds to over 30,000 messages per minute. So that was the data ingress rate that was required to make Phasor-based control work, and the DEGC platform facilitated it with ease. And here we have the 13 node feeder that we simulated using the Opal RT, and then also the PMU measurements and actuators for node 675. And the plots on the right demonstrate successful deployment of PBC using the DEGC platform. The top plot is the voltage, and the bottom plot is the voltage angle, or sorry, the top is the voltage magnitude, and the bottom is the voltage angle. And as you can see, the load profile has a number of disturbances. And even despite these disturbances, the PBC feedback controllers are able to track the phasor target, both the magnitude and the angle. And as you can see, the DEGC platform was able to handle the ingress of the PMU measurements without any issues to provide this successful demonstration.
So lastly, we want to give you some of the statistics for the actual deployment. So over the course of around a 27-day period, we measured a 99.9% delivery ratio, which is pretty good considering that over 350 million messages were delivered during that time. We also measured the overhead that the security solution and the message bus imposed. And in the situation where we had a message from a server on the UC Berkeley campus going up to the Amazon cloud and then down to the lab deployment for the HIL, we measured a median latency of a little less than 9 milliseconds and a 99th percentile latency of a little over 10 milliseconds. So we're feeling pretty good that this is sufficient to implement a wide array of control. And this was all executed with a single cloud-based broker. So this is the amount of reliability we're getting without taking sort of special extra steps to provide, fallback brokers and the rest of that. Here's a brief time series on the messages published per hour over the course of that deployment. You can see the dips where the message delivery ratio dropped. Because those outages were less than an hour, the rate doesn't actually drop all the way to 0. You can also see a slope from 6.3 to 6.10, where due to some clock synchronization errors, a certain amount of the micro PMU measurements were getting lost and then not being delivered onto the network. But all in all, it sort of delivered, was able to handle the data rates fairly well and deliver everything promptly. And so, in conclusion, we've introduced the DEGC software and communication platform, which implements secure and reliable communication for DER management and control. We've demonstrated this in a hardware in the loop setting by implementing the PBC framework. And we've shown and measured that the software architecture is not just effective in implementing these different control applications, but that it's actually possible to run these kind of applications over a secure and reliable message bus. Which makes it it's a great primitive for doing this kind of agile deployment and development to encourage the kind of innovation in DER control that we'd like to see. We also want to point out that the DEGC platform is open source. We've provided a repository online on GitHub that links to all the different other sources. We encourage you to check it out, and thanks for listening to the talk.